Okay, so we have one last talk for the session. We wanted to pull in some more of the recent work on diffusion connection to LLMs. This talk is from Gianis Daras, who is a postdoc at MIT. He's going to talk about learning generative models with corrupted data. So thanks so much for coming.
Perfect. So hello, everyone. Thanks a lot for staying for the very final talk. So today, I think we're going to talk about this cool problem of how do you train generative models when some of your data are corrupted. And this is a line of work that I have been pushing for the past 2 years with an excellent set of collaborators that I'm super thankful for. And let's get started. So if you want to train a generative model, roughly speaking, there are 3 steps, right? So the very first step is you have to collect some data. That's kind of easy. Maybe you go to the web, you get some data. And the second step is that you need to train the model. And then after you train it, you use it to solve problems. For example, Alex gave a talk on Monday. This is a picture of Alex corrupted, and then you would like to have a model to fix the picture for you. So these are roughly speaking the 3 steps. And I want to argue that a lot of the research has been going on the last 2 stages. For example, if you want to train a model, you have so many considerations. Are you going to use a diffusion objective or an autoregressive objective? Are you going to use a unit in terms of images, or are you going to use a transformer? And then you have to think about scaling loss. How big should I make my model? And then you train it, and then even after that, you have to do post-training. You have to do instruction tuning, reinforcement learning, and a lot of other things. And then even after you train and you do all of this post-training, then you're given a problem, and then again, you have to think about algorithms to solve the problem. In the context of LLMs, this could mean you have to do chain of thought. You have to change the decoding algorithm. In the context of diffusion models, this would mean that you have to come up with a diffusion model algorithm for solving these problems. And of course, there is the question of evaluation that we had a wonderful talk going over that question. So there is a lot of research going on in these 2 stages. But I want to argue today that the first part is actually super important. And I think it's actually common acknowledgement that the secret sauce behind the success of these models is in the training data. So everyone knows that if you don't have good training data, you cannot do really well. And then despite the fact that this is the secret sauce, I want to argue that the recipe that we are using is actually kind of simple. So here's how it goes. This is for example, from the work that we did in the Datacom paper. What you do is the following. You first need to form a very large data set. So for that, you might go to the web and you download the whole web. And then you go to other proprietary source that you might have, and you form this very big pool of data. And then this data has a lot of problematic elements. Maybe it has NSFW content, copyrighted content, duplicates, whatever. So you want to remove all these bad things. And then even after you remove a lot of the data set that you have has low quality samples. So what do? You come up with some pipeline of scoring your data points. It can be as simple as asking clip or asking some LLM to score your data points. So you score all of your data points, or it can be something much more fancy, like the meta-gradient algorithm that Andrew talked about yesterday. And then after you have scored all of your data points, you essentially say, OK, whatever is below that threshold, I'm not going to use it. And whatever is above that threshold, I'm going to use it. So that seems to be the winning recipe that has gotten us very far. I want to argue now that this winning recipe has some issues. And there are certain cases where it can be really problematic. So let's see some of the things that could go wrong. Okay. So the first thing is OK, for images, it makes sense. There is tons of data in the web that you can download. But if you actually want to apply these scientific applications, that's not usually the case. For example, if you want to do MRI, you will go to the fast MRI dataset. And if you want to do MRI for brains, you will find 7,000 samples, which is very far away from the 12 billion images that you would train on your text-to-image generative model. If you want to do proteins, you will go to the protein data bank. And again, you're in the order of thousands. And these samples are really expensive. They correspond to someone doing a PhD for you, spend 5 years of their life to crystallize a protein and put it out there for all of us to use. And of course, it's really hard to scale that to having 7 billion PhDs. So that's a challenge. And if you want to do black hole imaging, good luck, because you cannot even have a full perfect sample. So this recipe of like collecting a very large pool of data, especially high quality data, can be really challenging for scientific applications. The second thing is that like even for images, I want to say that like different data points have different utilities, and that poses a dilemma. So for example, this is a data set that is used to train like text-to-image generative models, and these are some of the very bad quality data points according to CLIP. So CLIP thinks that these images are not very informative, and I think it's right, because here are some images that are in the same data set that are great. So when people like train their models on these data sets, they usually treat all of these points as the same. So the low quality points and the high quality points are all like in the same data mix and the same algorithm, and then they all contribute the same to training the model. And don't go very far, because this happens to your favorite ImageNet dataset as well. There are tons of bad samples there. And there are also very good samples in ImageNet. And in the context of text, you know, like you go to the web, and then you will find some textbooks from UMES, for example. But then you will also find data from Reddit user 3345. And all of that will get to your dataset, and then you will have to train your LLM on them. So there are different utilities, right? And you're facing the following, yes? Yeah, like, for example, you would probably want your LLM to be able to like do complex proofs. And when you train your LLM on a bunch of data, some of them, they're very close to proofs because they are like textbook data and stuff, but some of them are just discussions on Reddit from like users that have like, I don't know, typos, like not very rich semantical content, et cetera, et cetera. And similarly for images, you would like your model to be able to produce this type of images, but in your data set, you also have this type of images. So in that sense, like you have like some high quality data that could come from a very skillful.
Like I look at that low quality data, I can still figure out what's in there.
Right. Exactly. That's exactly the point that I'm getting to, which is exactly this dilemma, right? So you want the low quality data because like you want to be like robust, and you want to get the diversity that there is in this data, and you want to be able to have like a model that can treat all of these things. But also generation time, you don't want to be like generating this type of things. For example, if you are training a text-to-image generative model, you don't want to be generating like images that have like low resolution, they have like different sort of artifacts, but you don't explicitly tell the model what is what, so you have facing the dilemma. Should I keep it in my data, or should I throw it away? So that's kind of the dilemma that you're currently facing. And if you look at like actual pipelines, what seems to be happening is that people are erroring on the safe side. So for example, like people that created Lion, it's a data set that has billions of image text pairs. What they did is they downloaded a lot of image text pairs from the web, and then they have a very complicated pipeline to remove stuff, and they ended up removing 90% of the data set. And then for protein generative models, we're going to come to that in a little bit, but people also like throw away like tons of the data. Cool. A final point is that like there is a lot of sensitive data that we are sometimes training with, and we should not be doing that. And that's especially problematic because diffusion models, in particular, they memorize a lot their data sets, much more than other like generative models like GANs. And you can do this very simple experiment. Just take like a small data set of 300 images and train a model, then generate a bunch of samples, and then look at the nearest neighbor to that samples, and then you will figure out that like you just invented a copy machine. So that's not a generative model, that's a copy machine. And maybe you argue, okay, this happened because like you just trained a model on 300 images. What if you trained on like billions of images? Is that going to be an issue? And then we saw that this is actually an issue. So we suspect that this model, Stable Diffusion XL, was trained on Lion. We don't know because they never released a data set. And we take this image that it's on Lion. And then what we're going to do is we're going to put a big black box. And we are going to ask the model to fix this image for us. So we're going to give the middle image to the model, and we are like, can you please reconstruct it? And then you ended up getting this. So the model gave you like perfect reconstruction, which makes it very suspicious that this image has been used in the training set. And this is not like a thing that happens one time, but like happens across many different images. You can do similar things for language models. we have this recent ICLR paper where we saw that like a bunch of books have been used in the dataset of Llama 3. Cool. So there are a couple of challenges. And because of these challenges, if we had a way to use low-quality data, that would be great, because those are easier to acquire. Sometimes they're cheaper. And also, a lot of the times, they're copyright-free. So this is what we are going for. We're going for a framework that would be able to use bad quality data that are easier to acquire, cheaper to acquire, and maybe copyright-free, hopefully copyright-free. So that's going to be like the focus of the talk. And we are going to do this progressively. So we are going to start from a very toy mathematical setting where like the data will be corrupted by additive Gaussian noise. And I'm not doing this because I want to tire you with the math. I'm doing this because we're actually going to use this. So we're going to start from this like mathematical framework. We're going to start on developing the tools. And then we'll generalize these tools to arbitrary corruption that we see in the web. We will see what kind of assumptions are needed to be able to use this framework. And then after we have the hammer, we're going to start like applying these two things. And I'm going to show you like at least 2 applications, maybe 3. One is in proteins, and the other is in memorization. And if I can talk about image generative models, we'll talk about that as well. Sounds good? Perfect. OK, let's do it. So let's start with additive Gaussian noise. OK, before I do this, I will just give you like a maybe 1 minute or 2 minute overview of diffusion models. I'm not going to get a lot into the weeds. I'm just going to give you like the things that you will need to know. So this is an image of Antonio Torralba. He's one of my postdoc supervisors. And then in diffusion model, what you will do if you have an image like this and a distribution of image like this is you would corrupt them at different levels. So you start with an image that you assume that's coming from a good distribution that you care about, P0. And then you corrupt them at different levels. And then at a particular point, you look at this random variable xt that is like your image plus some noise. That's what xt is. That's the type of notation that we're going to be using. And if you want to sample from all of these things, all of these like intermediate noise levels simultaneously, it turns out that there is a way to do this by following a stochastic differential equation that does exactly this. It just adds progressively noise more and more to your image, starting from your clean image and going all the way up to something that's like very close to a Gaussian. So in this notation here, BT is the Brownian motion. Cool. Now, the cool thing about this and this mathematical notation is that like you want to reverse this process. So you want to start with something that looks like noise and start building your way all the way up to clean images. And it turns out that there is like a beautiful mathematical result that says that the reverse of this stochastic process that we were talking about before is also a diffusion process. So there is like a Markovian process that you can start from like this terminal distribution that you arrived before and run it all the way to get clean images. And to do this, you need this quantity, which is the gradient of the log likelihood, also known as the score function. So all that you need to do is you need to be able to sample from this terminal distribution. This almost looks like a Gaussian. And then after you can sample with that, you can initialize your system. And then you run it all the way up to the clean distribution. So to do this, you need this score function. And then you run your reverse SD. Of course, there are going to be like a lot of errors. And Sitan Chen and others, they have beautiful works analyzing this type of errors. There's going to be like the score estimation error, the fact that you're going to have to discretize the SD, and also the fact that the initial distribution is not a pure Gaussian, but you're going to have to start with something that you can sample from. So there is this error as well. Anyway, we're going to forget all of these errors for the context of the talk. And all we're going to think about is the fact that we want to learn the score function. And there is this beautiful connection that connects the score function with this easy object. That's a very interpretable and easy object, which is the conditional expectation. In other words, it's the best noise that we have in the L2 sense. So what does that mean? It means that I give you like an image, this image X. And then if you want to find the score, what you need to have access to is you need to have access to an object that tries to denoise the image. It gives you the best prediction for the clean image given that noisy observation. And the conditional expectation, you can learn it by solving this optimization problem, assuming that you're optimizing over a rich enough family. Make sense? This is all that we're going to need from the background of diffusion models. OK, now let's start talking about interesting stuff. So in our setting, we assume that we live in a very cruel universe that does not give us good samples. Instead, we're going to be sampled from this distribution PT nature. So nature decides to give us noisy samples at a given known noise level. And again, I'm starting with this very stylistic corruption, but we'll work our way to like more realistic things. Cool. So now the goal is to have a model that can sample like great images, like the ones on the left here, given only a noisy image at this particular noise level. That's the goal, and that's the hope. Now, following on the discussion that we were doing before, we said that in order to learn the sample, we need the score. And there is this duality between the score function and the conditional expectation. So if we want to sample, the only object that we need to care about is we need to find this denoiser. But we need to find this denoiser for all the times. That includes times that have more noise than the noise that there is in our data set, and also times that have less noise than the noise there is in our data set. And for that regime, we have no data at all. Because we can always get our data set and add more noise to it. It's still challenging to learn the denoiser, but at least we have the inputs of the network that we are trying to train. On the other side, we have no inputs at all. Cool. So these two problems, we're going to treat them separately. So let's start by the easy one. The problem of I give you some data from the distribution T nature, the noisy data that nature gives us, and you are trying to learn a generative model. And to do that, you need this conditional expectation for times T that have more noise than the noise in your data. Make sense? Perfect. So here's like a funny result that you can prove, which is actually like pretty intuitive, I guess, but can allow us to do like cool things. It is the following thing. So on the left side, what you have is your best prediction for the noisy image at the level of noise of your data set. So that's your best prediction for this T nature. So you see an image xt, you see like this image xt, and you're trying to find the best prediction, not all the way up to clean images, but just up to images at the noise level T nature. It turns out that this thing is somewhere in the line between your best guess for the clean image and the current noisy image that you are. If you want to do like a kind of a sanity check, for that, just set the time t to be the time T nature, and you are just going to see that like your best guess for your T nature image is like the point that you are. So that's this little formula. It's easy to prove that we're going to show it in a bit. And then if you do a little bit of rearrangement of terms, it gives you like a pretty interesting corollary, which is the following. The best denoiser for the clean images, that's what you care for. You care about the left-hand side. This is the best denoiser for the clean images. It is just like the best denoiser for images that are a little bit less noisy in the T nature noise level, and some other term that is like because it's your input, xt. Which gives rise to the following laws. On the left side is what we usually do, right? So what do you usually do? We have like two pairs. We have a very noisy image, and we have a clean image. And then we train our neural network with these laws. We give to the neural network the noisy image, and we ask it to predict the clean image. That's what we usually do. On the right-hand side is what we will do. And notice that the objective on the right does not involve at all clean images. Instead, we assume that we have two pairs. We have the super noisy image as before, and we have a cleaner version of that. And my claim is that because of this result before, if you optimize this objective on the right, you will find the same minimizer. You will find the denoiser that denoises all the way up to clean images without ever seeing a clean image. Yes?
In the previous slide, isn't there an assumption that you have a linear combination? The y should be linear.
Oh, I'm gonna prove this. So this is a theorem. Make sense? Perfect. Okay.
Can I see your proof?
Yeah, it is here. Okay, so this is it actually, the proof. Let's get the proof. The proof is actually super intuitive. it goes in the following way. You can write the noisy image into two equivalent ways. You can view it as a clean image plus a lot of noise, or as a noisy image and a little bit of noise. OK, so far I didn't do anything great. I just said that there are two ways to view my super noisy image. As something clean plus a lot of noise, or something like less clean plus a little bit of noise. Now there was this Swedish formula that was connecting the score function with the best denoiser. And that Swedish formula was actually pretty general. It tells us, you have a random variable y, it is x plus some noise, and this thing holds. But now we have two equivalent expressions for xt, our noisy image. So we can apply this formula twice. And if you apply it twice, you get two different expressions for the same score function. One of these expressions involves the conditional expectation for the clean image that you care about. The other is coming from the second way to view your noisy image that connects it to the conditional expectation of the noisy image. But the likelihood did not change. We are talking about the same variable. So these two things are equal. So by just combining them, we get this thing that I had before. Make sense? Cool. So maybe it's a little bit counterintuitive, but essentially what this is telling you is that to denoise, all you need is the direction of the noise. So that's what you care about. You care about what is the direction of the noise, and if you want to denoise more, you just scale it appropriately. So that's what this result kind of tells you. And this is very particular for Gaussian distributions. If your corruption is not Gaussian, this is not true. Yes?
Can you provide a little more insight into why the direction of the noise is sufficient?
Oh, right, because essentially the score here is your prediction for the noise. And then because it's you can think of this conditional expectation as your prediction for the clean image minus your noisy input. So what is left is your noise rescaled. So this is how you go from the one to the other. So this is what the result tells you, that to denoise you need the direction of the noise. And this allows for this cool objective. Yes?
So could you remind us what sigma Tn squared?
Right. So this is in this cruel world, you are given data at a particular known noise level. You know that it's a cruel world, and you know exactly how cruel it is. So you know that it's coming from an additive Gaussian noise at a particular noise level. And sigma Tn is the variance of the noise that you have in this data. Yeah, that's known. Good. And we are thinking that there is a single one for now. So we are very stylistic, but things are going to get very interesting very soon. Yes?
To apply all this, you need to know the noise level of...
Yes. Yes, you need to know this. And it has to be Gaussian noise. So these are all very restrictive assumptions that we're going to start lifting one by one. OK, cool. So perfect. OK, so let's start to become a little bit more realistic now. In reality, your data points, as I told you in the beginning, they have different utilities. So that means that you get a bunch of images, and each image carries its own noise level that you can use it, essentially. And because this is my other postdoc advisor, so I made him have the full noise because I know that he's not going to be offended. And this kind of plot is going to tell you exactly why the images have different utilities. Because, for example, if an image has a lot of noise, you are only allowed to use it for the very high noise regime. Because this trick that I told you was only working for noise that has more noise than the noise in your data set. Now, if another image has less noise, you are allowed to use it for more times. So very intuitive that it gives you higher utility because it allows you to learn more denoisers. You can use it, and your objective will learn more denoisers, and so on. Cool. So this will give rise to a very simple way of training with noisy data that has two line changes in your normal diffusion training objective. So what do you use normally? You want to update your parameters. So what do? You sample an image from your data set. That's your clean image. Then you sample a time. You decide how much noise you're going to add. Then you add that noise to your image. You create your noise image. And then you train your model to predict from the noise image the clean image. So that's the usual pipeline. So now we're going to flip the first two steps. So first, we're going to decide how much noise we're going to add. And then not all of the images in our dataset are eligible to be used for this noise. Because as I told you before, some images can only be used for a particular set of noises. So I have to go over my dataset and find an image that I'm allowed to use for this particular noise level that I want to train a denoiser for. Perfect. So I find this image and this noise level. This is xt nature is an image that has less noise than the noise level at time t. I add the extra noise, and then I train with my loss. And that's it. OK, makes sense. And this objective does not require clean images. It can work. So when you train your model, when you're trying to form your bats, you just before take all of the images. Now you have already decided your noise level, and then you look at the first image. You're like, can I use it? Or if not, rejection sampling. I throw it away. I go to the next one. And then so you have you're just going over your data to form a batch. And if the particular image cannot be used in this time that you want it, you just put it aside, and then you're I'm going to use it later.
How do you decide?
Oh, it's just you just look at these images come with annotations of how much noise they have, because you know the noise level. Okay, yeah. So I guess I get your question now. So you know the noise level for all this for each image. Perfect. So there are a bunch of problems with this approach. One problem is that for this particular region, you only rely on a few clean images. Because the trick that I told you, you can only use images that have noise more than the noise level that they are in the dataset. So there is this small regime where you don't have a lot of images. You just rely on some clean samples that you might or might not have. And there are two natural questions. First of all, how many do you need? If I don't have a lot of images that are super high quality, is my whole performance going to collapse? And then there is the question of what do I do if I don't have any? Can I still do things? So for most realistic scenarios, 2 is not a very realistic setting, because if you pay enough or if you try enough, you can't get your hands into some high quality samples. But we're still gonna try to solve this. So I'm not gonna prove this, but I'm gonna show you a quick way of doing this. So here the setup is that I'm trying to find a denoiser at a time t prime for which I don't have data for. I only have data times t nature, and t is maybe a little bit more than t nature. But I want to find a denoiser at time t prime. And I will set up a loss that will allow me to learn this denoiser without clean data. So here's how this is going to work. So you have a model that you have trained so far. And you ask your model, hey, model, can you give me your best prediction for the clean image at time t? And it gives you this blurry image. Why is it blurry? It is blurry because it's so a very noisy image, so there could be many plausible explanations, right? So there could be many things that generated this. So it gave you some sort of average of all the things that could have happened. Great. Then you use your model again to sample a bunch of images at this time t prime. So if you ask me, why is the model good here? I don't have samples. I'm going to tell you, just trust it. It's going to do something. Whatever it does, just you arrive at these other samples. And then for each one of them, they're different because you're using a stochastic sampler here. You're using this reverse SD that we defined before. And then for each one of them, again, you can ask hey, model, what do you think is the clean image? And then you get 2 more predictions. Now you can average those predictions. So what is this prediction? Is a blurry image that you get from the average of the predictions at time t prime. Now what I want to tell you is that a good model would satisfy this property. It would be self-consistent. So what is a self-consistent model? Is a model that agrees with itself on expectation. So if at time t you had this blurry prediction, then if you look at a new time t prime that has less noise, you have a bunch of different points. For each one of them, you have a prediction. On average, you should agree with your previous self. So you should agree with the previous prediction. It's very easy to see that the conditional expectation, which is what we are going for, satisfies this property. The harder part is to show that if you had the conditional expectation here, that's the only solution that satisfies this property. But it turns out that this is true. And we have a paper that we saw this theorem. It was kind of surprising to us as well. But for now, just take my word for it, for the interest of time. But the algorithm would be just like what I described. It would be that like you just take your model. If you want to find the denoiser at time t prime, you take your broken model. You generate a bunch of samples. For each one of the samples, you take the prediction. The average of the prediction should match the prediction at the time that you trusted. And if a model satisfies this, things are going to go great. Yes? How does this again?
How are you sidestepping the data set coverage problem? Like if you don't have, samples with a particular noise, if you don't have good coverage, like kind of.
Yeah. So essentially, yeah, the intuition behind this is that like the distribution at time t uniquely determines the distribution at all the previous time points, because it's some sort of a deconvolution problem.
So the consistency is basically helping you rule out other possible future models.
Exactly.
And then the proof is basically saying that like there is one unique solution.
Yeah, you find a test function that should be true for the best model. So like this property, you can verify that if I put here the conditional expectation by the entire law of expectation, this will be true.
So how many T's do you need beforehand before you can like rule out?
This needs to hold for all the pairs of T's. But you can do it locally, because local consistency implies global consistency. So you can take like T's that are like next to each other to avoid like running a big engineering training. Cool. Okay, cool. I don't want to spend too much time on that because it's not going to be super relevant for the rest of the talk. I just want to show you like some cool like results with this. So what we did is like we took a pre-trained model and we are like, let's see if we can at least fine-tune it with noisy data, the particular data set. So this is a latent diffusion model. So this is what you get if you just encode the images, and then this is what you get if you start like encoding the images and then you start add noise to the encodings. And if you want to see like what the best model would do if you run posterior sampling with these images, that like you see the reconstructions on the last row. So like this is what the best model would do, and you can see that like the more noise you have, the less the model like outputs resemble like your initial image. So what we did is that we did a bunch of trainings at different like levels of noise. And for the first run, we did not use consistency. And what will happen here, and this is what actually happens, that like the first row, when you don't have noise, you get good samples. As you start adding more and more noise, the samples look like ghosts. Why they are ghosts? Because they're like some blurry things in the latent space. So the model outputs gives you like this like ghost-like images. If you add consistency, you recover back some of the details. So the images like become less ghost-like. They're still not perfect, and you can actually measure this. So FID is a measure of performance for image generative models, and then you can see as you change the training noise level that like FID goes up, but at least with consistency, the orange line, you maintain more of your performance. And then also memorization decrease, but I'll get to that in a bit. And then we also did this like for text to image data sets, and then you still like you get like a reasonable model even though it's trained like noisy data. A valid concern, and I can hear it coming, is like, okay, but you just started with a model that was trained on good data and then you fine-tuned it. So we repeated this experiment with a model from scratch. So we went to these like academic data sets, and then we created data sets at different like noise levels synthetically, and then we trained models. And then what we consistently saw is that we still like produce valid samples, but the performance decreases as you would expect because you are limited by the number of information that you have from your noisy samples. So this method, if you don't have any data, that's the best you can do maybe. But if you can't get your hands into some high quality data, you are advised to use them because you are going to get like decreased performance. And then same things you can do for linear measurements, but we'll skip that part for the interest of time. OK, cool. So there is one thing that like we want to answer before we generalize this to arbitrary corruptions, which is the fact that like before we said, okay, like here we could use like an objective for the low noise times. You could use an objective that does not require like high quality images, but that's like an objective that maybe will lead to decreased performance. So what if we just rely on a bunch of good samples? So we look at this setting where we have two sets. Okay, to simplify things, there are two sets. So we spent some amount of money, effort, you name it, to obtain a small set of high-quality samples. And then we got a bunch of like noisy samples. So we have an asymmetric setting where we have like a lot of noisy samples and a few good data points. And on these times, we are going to use all the data. For noise level that has like more noise than noisy data points, we're going to use all the data. For these other times, we're only going to rely on the few good data points that we have. And we're not going to use consistency just to make things like simple and fast. And then it's the question of like, how is this going to perform? OK, so this is what you get. So we do this experiment, OK? And then we start with 100% of the data. Then we train a model on CIFAR10, CELEB, and ImageNet, and then we get the performances that other people are reporting. So this would be the state-of-the-art numbers like a year or two ago on these data sets. Then we are like, what happens if all of your data is noisy at a particular noisy level? And then you see like very bad performance. And the reason you got really bad performance is that even though like you used like our method, you were limited by the amount of data that you had. The information that you had in the noisy samples was just not enough. Then another like baseline is what if we just use like a 10% of high quality data. We don't have access to the full data set, but we have access to a subset, 10% subset of the data, and then we train on this. And then you see that the performance is even worse. And here's the surprising part. If you combine 10% of high quality data and 90% of super noisy data, you get back almost all of your performance, which is like, I think, pretty crazy because these other two baselines, 100% noisy data, not great. 10% very clean data, also not great. But this combination of like 10% clean data and 90% noisy data performs really well. So that means that maybe you can rely on like a few super good points to learn these like details that make high quality images. And you can use the bulk of like noisy data points to learn the noises for these other noise levels that look at the image at some other scale, but doesn't need to look at these images, at these details. And that's like a key takeaway that we're going to start using now. And the other interesting thing is that we kind of like got obsessed with this. So we ran like 200 experiments at different like data settings. And then we created like gigantic tables that were like, OK, what happens if I have 20% noisy data points at a particular noise level and 80% clean data points? And then we had like all of these mixes of data points. And that kind of allowed us to get some prices for the noisy images. And how do you do this? You go and look at, for example, at these 2 points. So one point is what you get by just using like 70% of clean data but not noisy data. And the other data point is what you get by using 50% of clean data and 50% of noisy data at a particular noise level. And then you're like, oh, this FID is lower, so the performance is better. So if there was a fixed price, I would have to pay less to obtain the red box than to obtain the green box. And you start writing down like inequalities like this. So you're like, 70% of my data set clean price should be less than 50% clean and 50% noisy. And if you write down all this set of inequalities and you like find like the tightest inequality that you can get some sort of like prices for images. And it looks like that the noise, an image for ImageNet at noise level 0.2 is actually not that bad. Because it's better than like 2 clean images, for example, assuming you have a small good set of clean images. If you don't have this, like this whole fixed pricing scheme breaks down. Cool. OK, so now that we have kind of built it for this like toy case, I'm going to start showing you some applications, and then I'm going to show you the generalization and what this allows. But the very first application does not require any generalization. We're just going to use this framework. OK. This framework is going to help us answer a very interesting question, I think. This is a recent paper that we submitted to ICML. And the question is, does generation require memorization? This is the question. Do I need to memorize my training samples if I want to produce amazing images? So there are like a bunch of like negative and pessimistic results in that landscape. So we initially thought that it's probably going to be kind of like impossible. So the very first like negative kind of indication was this like conjecture by Callini. So Callini and et al., they have this paper extracting training data from diffusion models. So they design an attack on how you extract training data from diffusion models. And then they notice that diffusion models memorize so much. And then they even write that it is possible that diffusion models are so great because they memorize. And they have this conjecture. They believe that maybe the reason diffusion models are so good and they outperform GARMs and other approaches is that the fact that they can memorize so well their data set. And that was a conjecture. And this kind of goes along with this result from Feldman, which is a known result from memorization in classifiers. So if you have like a very particular model about how your data arise, you can actually show that it pays to memorize. In particular, if you are thinking of like a case where like you have a data distribution with heavy tails, you can think of like, there are like different things that can happen. There are like different types of dogs, cats, and so on. And then you have like a fixed data set of size n. There are like many things that will have like probability 1 over n to appear. Many classes that have probability 1 over n to appear. For example, a particular type of Labrador can have probability 1 over n to appear. But also that holds for like another type of dog. And these have the same probability. And because of the fact that your data set is fixed, you are going to, on expectation, see one sample from these Labradors, for example, class. And that puts you in a very bad spot because you cannot distinguish between two cases. One case is that this class that you are seeing is actually a very rare class, something that never happens, like some super exotic animal you will never, like the probability of seeing this in your test evaluation is like very small. Or it could be like like a class that appears very often. It could be like dogs. But because there are many classes, you just happen to see like one of them in this fixed data set. And you cannot tell between these two cases, right? So if it's a class that appears often, so you better like memorize it. So that's kind of like the intuition behind this paper. And then the question is like, do these things like extend for generative models? And the key intuition here is that like, when you're having a generative model, like a diffusion generative model, when is the diversity of your sample going to be like controlled? At which point in the diffusion trajectory? And the answer is in the beginning, because in the beginning, like you kind of decide what you will generate, and then you fix the details. So in the beginning, you're like, I'm going to generate a dog. It's going to like position in this particular way. So you like decide the geometry, and then you like put the details. So if you can avoid memorization in this early stage of diffusion models where you decide the structure of your image, then maybe you will memorize the high frequency details, but you will still be able to produce like diverse outputs. So this is kind of like our hope, why we might be able to escape like this type of behavior that appears in classifiers. But it turns out that generative models that are trained on limited data sets, they actually do memorize even for very high noise. In particular, you give this input to a model that has like noise with standard deviation 17. It's like extreme noise. And then you ask the model, what do you think is your best prediction for the clean image? And on the third row, which is a model that is trained on like very limited data, you actually see very clean images. So the model sees these noisy inputs like, yeah, I know what it is. It is this particular clean image. So this is like sign of memorization at a very early stage of the diffusion model. Instead, if you have a model that's trained on more images, you get blurriness, which is a good thing, because it means that the model is unsure about which one of the many images could have generated this noisy observation. And we can use our method to actually do this. So how are we going to do this? We are going to like split our diffusion times into two parts. In one part with high noise, we're going to train with noisy data with our algorithm. And this model cannot memorize well because it has never seen like the clean samples. It has seen only noisy observation of these clean samples. So in this regime, we train a model with our ambient loss function, this loss function that does not involve clean data. And on the other regime, we just train with like a regular objective. And the intuition here is that like the diversity is controlled in this first like part of the diffusion trajectory. So if at this first part we manage to escape it and generate like diverse outputs, then this part that has memorized, it will just like memorize the details, but it will not just like completely change our diverse image. So that's kind of like the algorithm, and it turns out to actually be true. So you can show on a bunch of different settings. So for example, in this plot, you see like FID. FID is a measure of like performance. And then on the other axis, you see like memorization. And then there is this intuition that there is a trade-off between like how well you can do and like the memorization that you get. Of course, you can just always spit out like random samples, and then your memorization is like almost 0, but then your performance is going to be like super bad. And this red point is what like usual models would give you. If you just train a diffusion model with a regular diffusion matching objective, this is what you're going to do. This is what you're going to get. Yes? That's a great question. So in this example, in this case, what we do is that like we have like the whole training set, the whole like set of images. We just give to the model like a small subset of these images. Then the model is trained with this and generates samples. And then for each one of the generated samples, we look at its nearest neighbor in the data set. And if like the nearest neighbor is like very close, we define it as memorized. And then we look at the amount of points that are actually memorized. And the nearest neighbor thing is happening in some latent space, in particular in the latent space of dyno embeddings, which is like what people do in this work in general. Perfect.
And your noise is still Gaussian here.
Still Gaussian, yeah. So here we had clean data. It's not like we intentionally corrupted our data because we wanted to achieve better trade-offs between like memorization and generation. And this also happens with text-to-image models. And then you can see that like there is some memorization coming from the text, because if the text-image caption pair is like unique, you can just look at the text and know what the image is. So there is some memorization coming from the text, and there is like lots of prior work in how do you mitigate this. But there is some memorization coming from the images themselves, and this is like what our algorithm does. So if you combine these two things, you manage to improve to all of these like established benchmarks. So cool. So this was like one thing that we used our framework for. Now let's use it for like more useful things that are realistic corruptions. In the web, you're gonna see things like these. They're images that are gonna be like severely compressed, and they have like motion blur and other sort of artifacts. And so far we have been just dealing with like additive Gaussian noise. So how are we gonna like treat these kind of things? It's a great question. So for that, we're gonna play a game. So I want your help with that, okay? So we see two images. On the left, we have like a clean image. On the right, we have like a blurry image. Okay, I'm gonna be showing you now two new images, but with noise. And I want you to tell me which one do you think is the blurry and which one do you think is the clean. So raise your hand if you think that the blurry is the one on the left. Okay, you got it right. So that's the blurry, the noise with red, and that's the clean. Okay. Now we'll increase the noise. Which one do you think is the blurry and which one do you think is the clean? Raise your hand if you think that the one on the left is the blurry. Okay, you can still get it. Perfect. All right. How about now? This become like more difficult. Like which one is the blurry and which one is the clean? Who thinks that the one on the left is the blurry one? Okay, so now we have like some disagreement at least. So the one on the blurry was on the right. But the point is that you know what blurry and clean is. They are like different things when you have no noise. But noise is a contracting thing. So like as you add more noise, everything is gonna come closer. And essentially we are thinking of like this picture, okay? So there is a distribution of clean images, and there is a distribution of blurry images. And as you add more and more noise, they're all gonna converge to a Gaussian. But there is a point that these two distributions, as they're going to the Gaussian, they actually come so close so that like samples from the blurry distribution plus noise are useful because they are like looking as coming from the clean distribution plus noise. So the whole framework that we have been developing, we can still use it if we just go and replace our blurry distribution with this blurry distribution plus noise, so that it has like enough noise level so that it looks like our clean distribution plus noise. So that's what we are going to be doing. Okay. So essentially, if you're given like an image like this that is blurry, of course you cannot use it as clean. But if you add enough noise to it, it might look like a clean image plus noise. And then if it is the case, then you can just plug it into our algorithm and then start using these images.
But that assumes that your noise distribution, your additive noise, is a different distribution than your blur, right? So if my noise model is blurring itself.
So the way I add noise is always additive Gaussian noise. This distribution can be blurry, can be something else, and then we're going to look at what works, when it works and when it does not. If it actually always works, the question is that, like, are they going to merge when they become like pure Gaussians? Because if that's the case, it just becomes like filtration. So like the thing that people are doing, which is that they filter out samples, is exactly what this algorithm is going to do if the point that the distributions merge becomes like the very final point. Because essentially you're only going to be using this image to learn like the Gaussian. So this image is going to be like useless. But for a lot of cases, for example, Gaussian blur is a great case that works really well for this. And essentially, if you have like high frequency corruptions, this method works really well. If you have other types of corruptions like masking, this thing is not going to work as well.
I was thinking of something like edge distortions, for example.
Yeah.
Then I'm not sure what starts to happen.
It is true. And then like you're also not always constrained to be using additive Gaussian noise. So you can think that I will start corrupting and I will train an exotic diffusion model that learns to reverse some other process. But for now, we're just going to keep it as simple as possible. And this is actually like one future work of this. So I'm just going to show you this application. This is probably the most exciting thing I've done in my life, research-wise. I want to show you like an application where this works actually really well. And that application is like proteins. So if you remember from the beginning of this like talk, I motivate the fact that in some scientific applications, samples are actually really expensive. So proteins is just one of these applications because samples correspond to like someone doing a PhD. So essentially, we have like, roughly speaking, 20,000 unique proteins that correspond to like people doing their PhDs, and these are like super high quality data because someone like actually made them in the lab. And what are these data? Just to make it clear, it's like a protein is defined by some amino acid sequence, but then it looks somehow into space. If you fold it and it has like a geometric shape, and like we know 20,000 different like valid geometric like foldings that happen, but we want to be able to sample new ones to develop drugs and for other things. But the problem is that it's actually not very easy to do this process in the lab. It costs like a lot of money, a lot of expertise, and the harder the protein it is, like the longer the protein it is, the more complex the protein it is, the harder it is to actually make it. So it's not only that we don't have a lot of data, but also we have like a lot of like proteins that are like short, but we don't have a lot of proteins that are long, and we also have a lot of duplicates because people study like particular proteins that they're like useful for cancer or for something else. So when people like treating with protein generative models, what they do is they rely on synthetic data, which is actually pretty interesting because getting sequences for proteins is easy. Getting the actual 3D structure is hard. So you have 20,000 really good samples that are like actual structures that you made in the lab, but you have like millions of sequences that you have found in a cheap way. So what do? You ask AlphaFold to make the structures for you, and you create this data set that has like 20,000 like real proteins and like millions of proteins from AlphaFold. But of course, AlphaFold is a model. It makes mistakes. It has learning errors. So what you do is you filter based on like how much AlphaFold is confident about its predictions. And most of the data that AlphaFold generates, you throw it away, and then you just train on this remaining training set. Does that make sense? That's the setup. So if you look at, so these are like two metrics. On the left, you see like the quality, and on the right, you see the diversity. And then the horizontal axis is the complexity, like the size of the protein, essentially the complexity of the protein. So for longer proteins, what you see is that like the performance for both like quality and diversity goes down. Why it goes down? Because we don't have data. The AlphaFold data are not very confident. Like AlphaFold is not very confident for long and complex proteins, so we throw all of these away, and then there's like nothing to do there. So the performance becomes like horrible. But the proteins that are actually like important are these proteins, and those we cannot generate because the bigger proteins are the ones that appear in the human body and other stuff. So NVIDIA was actually like trying to solve this problem for a while. So they have this ICLR oral to appear like in a month in Singapore, or even less actually, maybe 2 weeks. And their approach was like, okay, we are actually gonna like try to make the model very big, and we're gonna apply different like filtering strategies. And by doing this, they actually managed to maintain a lot of the performance. So again, on the left, you see like the quality. On the right, you see the diversity. And then you will notice that like it still goes down, but it goes down like slower. So all these other like baselines, and then they managed, the green curve is what NVIDIA did, and this like was a big deal. So it got like an oral for ICLR, in ICLR for this. Instead, what we are gonna do is we are not gonna throw away any data. No data is gonna throw away. Every sample is gonna be important, but we're gonna start using the data as noisy data. So in particular, you have these proteins that you would usually throw away. So instead, what we are gonna try to do is we're gonna map each protein to its noise level, and we're gonna be using proteins differently based on their noise level. So if a protein has like low PLDDT, which is alpha-fold confidence, we're gonna be using this for only a subset of times. If it has like higher PLDDT, alpha-fold is more confident, we're gonna be using it for more times. But we're not gonna throw away any data. All we need to find is we need to find this mapping between like PLDDT, like the alpha-fold confidence, and time. And don't worry about how we find this for now. Let's assume that we have it. And then this is what you get. Like these points here are our models for short proteins. And these two axes, one is like quality and the other is diversity. So we dominate the whole Pareto frontier of quality and diversity by doing this, but this is still for short proteins. How about long? So for long, you see this. The green curve is ours, blue curve is NVIDIA. And our model is like 17 million parameters. NVIDIA's model is 400 million parameters. In designability, which is like the quality, we're a little better all over the place. But in diversity, we are like 30 to 40% better from NVIDIA's latest paper, just because we managed to use all of this data that was thrown away. And for a reference, we started from this model with no modifications in the architecture, in like the training hyperparameters, just the same model. The only thing that we changed is how we use the data. So the message that I wanna give you in this talk, and finish with that, because I'm running out of time, is that good models should use bad data, because there is a lot of value in this bad data, but there is a catch. When you use bad data, you have to be clever about it. You have to treat them differently based on how you treat the clean data. So that's all for today. Thanks so much. Yes?
So just trying to understand this plot here. So you're defining diversity by aligning the proteins, and then
yeah, so like,
how are you doing it phylogenetically or something?
so this is like a standard metric that people in the protein space are using. This is like the equivalent of like FID for images, I guess. And yeah, like what they do is like they generate proteins, and then they cluster them based on like how they are in 3D space. And then, yeah, diversity is a metric that essentially tries to measure how many different classes you have.
And are these diverse proteins which you're generating stable?
According to designability, yes. Because
If you do molecular dynamics on it.
second,
If you do molecular dynamics on it, are these structures?
so like the ultimate test, I think you're bringing a very good point, is that all of these things, they mean nothing unless you go to the lab, I think, or you run some expensive software. But like actually the ultimate test is the lab. So this is what we're in the process of doing. But in terms of metrics, like people were like celebrating a lot when they managed to improve these things like for 5-10%. This type of metrics, they seem to be giving like a 30% improvement on this ill-defined maybe, and maybe not super informative metrics. So like the ultimate is going to be the lab, and we don't know yet.
I mean, even the lab is tricky, right? Because when you go to so many residues, you're going to have such large structures, they either may not crystallize, or even if they crystallize, you are only capturing one particular crystallized conformation. And you might be generating a different conformer.
Yeah.
So you might be different than the crystal structure, but that doesn't mean that you're wrong. You just have a different. So that's why I said, if you were to look for the run molecular dynamics on it and look for the stability,
Yeah.
you might have a strong argument that this is meaningful even if you don't experimentally crystallize it.
I think that's a good point. So I'm not like an expert on proteins. My background is like generative models, but I like from the limited understanding I have of it, I think you're right. There could be many conformations and like testing in the lab that you can. I think if you manage to crystallize an 800 amino acids like synthetically generated, like from a model generated protein, I think that's already a big deal. If you manage to do one of those, but you make a good point that like maybe some of them are gonna fail for some other reasons or. Yeah, so it's a complex, evaluation is complex, especially in this particular setting. I agree with you. Any other questions? Yes.
That's a super, super naive question.
Perfect.
Trying to, I'm not even sure. Let me start by making sure I understood something that you said. That at some point, it is actually by adding the noisy bit, you get a better quality than if you had 100% clean data.
No. Yeah, if you like always, if you can get like 100% clean, that's always better. But the problem is that clean is expensive.
Right, you had the 50, 70,
Yeah.
and at some point you had 100% clean data. It was just smaller. Therefore, because of the size, it's not as good.
So 100% clean was winning. Let's get back to this. So I think it was somewhere here. So 100% clean, lower here is better. And 100% clean had like 1.99, for example, for CIFAR, which is the best thing that you can get. Now, if you have 90% noise and 10% clean, you get 2.81, which is worse, but it's very close compared to what you would get if you had only 10% clean or 100% noise. So here the point is that like the combination is actually like, essentially, if I were to design a data set and I had a fixed budget, what I would do based on this intuition is that I would spend some amount of money to get some really high quality samples, and then I would spend the rest of my budget getting tons of bad samples. I think that's kind of the takeaway.
So this depends on the budget and on the size.
Yeah.
I was thinking, listening to this, is there a process in which learning how to fix a noisy one actually gives a benefit?
Yeah.
Rather than just, I mean, you use memorization, I probably think about something else when I say memory.
Mm-hmm.
But memorization in our world is not equivalent to trying to work with and learning something, right? So memory is not the same as learning.
Yep.
And I was thinking, is it the fact that you're giving your algorithm the opportunity to learn and how to clean a noisy data set has by itself point in making it better?
I think this memorization example was actually a setting where this happened. So there was no noise in your data set. You added the noise to your data set. And why did you do this? You did this because you didn't have a lot of samples. So you were afraid that if you just train naively on the limited amount of samples that you have, you're going to overfit. So you intentionally corrupted your data set. And that gave them benefit. So that is like, I think, one setting that what you are saying is true. Others could be other settings could be true as well. But I think from what we have seen, that's like one thing that actually like corrupting your clean data was actually helpful. Yes.
In terms of when you talk about this data acquisition mix, of acquiring noisy images versus clean images,
Yeah.
I think a lot of these assumptions hinge on the use of like Gaussian lens. But in the real world, when you acquire noisy images, they might just be like poor quality, but of a different kind. Right? So have I understood that correctly?
Yeah, you have understood this correctly. So our framework is our approach is the following: we know how to solve one thing. We know how to solve things that have added Gaussian noise. So whatever else you have, we are going to convert it to the things that we know how to solve, and then we're going to solve it. In that process of conversion, we pay a price. What is the price that we pay? That we corrupt extra the data that you gave us. So this is by no means like an optimal algorithm of using all the data, but it is a better thing than throwing them away. So if it is blurry, if it's something else that you see in the real world, like low quality or whatever, we will convert it to some corruption that we understand that we can develop math for. Then we're going to solve it. In that process of conversion, we lost some information, and that is the price that we pay for the fact that we did not know what happened to the initial. We knew that it was corrupted, but we did not know what happened. If we knew exactly what happened, If we knew that it's additive Gaussian noise, we have an exact method. If we knew it was like linear measurements of a known corruption type, like let's say that we know that it's like random in painting, then we can still develop exact methods. The moment that our method becomes inexact is when like we don't know what happened, so we have to pay a price, which is this conversion price to like something that we can analyze. Yes.
Yeah, I have a question. Do you have any ideas if this kind of technique transfers to large language models?
Perfect.
I'm also remembering your talk on compositional on compositions. I think it was yesterday, where I think his name was Jason showed that if you have a hierarchical multi-step learning initial steps helps to learn high-order steps. So like kind of initial steps would be the noisy data.
Perfect. I wanted to talk about it, but I didn't have time, so thanks for the question. So we are actually trying to apply LLMs. This is something that like started very recently, but we are seeing some very promising results, I think. So like we are gonna try to apply the same methodology, which is we are gonna first try to imagine a toy corruption. Then for this toy corruption, we're gonna create math. If it is another type of corruption, we're gonna bring it by corrupting it further to this type of corruption that we can analyze. And then we're gonna use it. So the question is, what is the toy corruption that we can analyze? And the answer is, it's the corruption that arises from increasing the temperature of the softmax when you do next token prediction. So in particular, if you give me like a high quality sentence, the empirical analysis reveals a strong association between economic inequality and political polarization across diverse populations. What I can do is I can start increasing the temperature of this LLM that produced this sentence. And then if I increase it a little bit, I get research findings show a considerable connection between the gap between rich and poor. Simpler. If I increase it a lot, I get rich and poor and order them, appealed, grid, blah, blah. So here I destroyed this completely. Here I still had some signal, but it was like lower quality signal compared to the top one. And essentially, like, like if you have high quality, like, textbook data and Reddit user 3345, they're all going to go to the uniform as you like increase more and more the temperature of the softmax, but there is going to be a point that they intersect, and maybe the point of intersection is actually somewhere that you can use.
So, you don't mind follow up. I'm also thinking about this in terms of reasoning. So when you have multi-step reasoning, for example, you have 7 steps, taking just 2 or 3 out of those steps.
Yeah.
Then figuring out if it learns to complete more like 10-step procedure.
Reasoning is the thing that we're applying this to. If you saw the open thoughts talk from Alex on Monday, like we're doing very similar stuff. We can talk offline for the interest of time, but yeah, it's very relevant to that. Yes.
I think when you say when you use 100% of noisy data, you don't get good performance. There might be a statistical explanation for that. So in the old days when statistics studied environment error model, we already know that if you don't have your validation sample, meaning that if you don't have a percentage of clean data, and then that model is not identifiable.
Yeah. So I think this intuition is right. For the additive Gaussian noise, it has this nice property that it is always identifiable by noisy measurements. But I think the sample complexity... So when you don't know the corruption, yes. When you don't know the corruption, you're absolutely right. Yes, absolutely, I agree. That's a good point. Thanks.
Okay, let's thank the speaker once more. Okay, with that, we conclude our workshop. Thanks, everyone, for sticking around this week. It's been really fun. Great. See you guys next time.